Good morning and welcome. Today we want to have a summary of the course, so we can only go into give an overview. To get more details, I recommend to you to go through your notes, maybe complete them by looking at videos, and then write down the essential things of the course. I'll give you an overview today, but as I said, I recommend you to do that yourself, more complete, as we have time now in 2 hours. So let's just start with the summary. I just follow now the course as it went and give a few comments. Introduction, that was mainly motivation, an overview. Point 2 was on PDEs, partial differential equations, and there we distinguished equilibrium problems. And those are elliptic PDEs. And the example that we studied and looked at later on also in much more detail was the 2D Poisson equation. And that is an example for 2D steady heat equation. If we have a source term, it would be with heat source. Having an elliptic equation means it's a jury problem. Everything is determined by the boundary conditions. So we have to give boundary conditions everywhere. You should be aware of the different kinds of boundary conditions. Dirichlet, Neumann, and the mixture is called Robin boundary conditions. The second class of problems that we of PDEs describe marching problems. There we distinguish two kinds. One is hyperbolic problems, and so as the name says, they are hyperbolic PDEs, and they are characterized that we have characteristics, certain lines where the solution can be simplified. For the linear advection equation, we can actually simplify it to an ODE. So that is, and there we had as examples the 1D wave equation. We did not go too much into detail, but Radar had a demo on that, which is a second order equation. We spent much time later on the 1D linear advection equation. There the characteristic is given by the velocity. We have u t c ux is equal to 0, and c the advection velocity. That is the slope of the characteristics. That is important for deciding on boundary conditions. Here, boundary conditions are only to be given where the characteristics enter the domain, not where they leave, because there we can determine the solution, going on the characteristic either back to the initial conditions or to the boundary conditions. And the more advanced example that we had here, and that we also studied in more detail, was the inviscid Burgers equation. Which is a model of the one-dimensional Navier-Stokes equation, or actually the Euler equation, because for the inviscid Burgers equation we don't have viscous effects, and we have neglected the pressure gradient. Also here it is important to know about the characteristics. There the slope is given by u, the unknown variable itself, which can be positive or negative. So that is determining also there the boundary conditions. The second class of problems of PDEs, and parabolic problems, parabolic PDEs. There, it's also, as the heading says, a marching problem. And there we have in space to give boundary conditions at all boundaries. Again, we have options there given directly on Neumann boundary conditions. Describing the value directly, describing the normal derivative, Neumann. The examples that we studied in much detail was the 1D heat equation, where we saw examples of what I just said, giving the temperature, for example, giving the temperature gradient. We also looked at the 1D convection diffusion equation. Actually, we also looked at the 2D in later part of the course. There we have a combination both of diffusion and advection. But since the second derivatives in space dominate regarding the type, it is of parabolic type, although it has a hyperbolic character inside the convective part. And again, the more advanced example on that class is the Burger's equation itself, where we have included not only for the inviscid part, the convective part, but also the viscous part, the diffusive part. And that is then a model of the 1D incompressible Navier-Stokes equation without pressure gradient. There we can study nonlinear effects. Also there we have to give boundary conditions at all boundaries. And usually in these classes here, Burger's and convection diffusion, we give boundary conditions where the characteristics enter at the inflow boundaries, and we prescribe the value directly boundary condition. At the outflow, we usually extrapolate. Say we say du dx equals 0, for example. So that is then an overview, and now what I said in the beginning, to get that then prepared for the exam, I suggest you to go through the notes and then say write down, if you don't memorize it, write down what these equations are, what the features are, what we know about the type, and what we can say about the boundary conditions. Next section was on sources of error in CFD. Very important. And there we distinguished several types of errors. Truncation error, that is, how well, for example, do we approximate a first derivative or a second derivative by a finite difference approximation. So there we usually insert the exact solution, Taylor expansion, and subtract what we want to approximate, for example, the first derivative, and find out that the truncation error. So that is because you can think of it to do that. For example, the first derivative, we need to approximate, for example, u at x plus h. For doing that, we could do a Taylor expansion, but to have that exact, we would have to use infinitely many. But when we do a finite difference approximation, we truncate at some point. That is the equivalent to what the finite difference formula that we are using. Central difference, forward difference, backward difference, whatever. So that is a very essential point. But another point that is often forgotten, but that we looked at in exercise 1, is the rounding error. Because when we do computations on the computer, a finite difference approximation, we can only do that with the amount of digits that we can represent on the computer. So that is limited. That means we have only a floating point representation of numbers. For integer numbers it's no problem, but for real numbers it's a problem. So that leads to rounding errors, and you might remember the problem from exercise 1, where we had the grid spacing, well, a write it in a logarithm here, logarithm of h. We had a couple of here, and we had here the total error of the central difference. So here is the total error, for example, of the central difference for the first derivative. And then we got graphs, and say what we have here, 0, -2, -4, -6, and so on. I think I should extend it a little bit to the left. So -8, -10, something like that. Then we had graphs looking like roughly like that. They go down, and in this part it is the truncation error determining it. So they have a slope here that indicates that the approximation is of second order. So as we decrease h, as we half it, the error is decreased by 1/4. So that we can see in this slope. But then, at some point, and actually in the exercises the week, let's see, before Easter, I gave an analysis where this minimum is. We can determine that, but that is outside the pencil. Nevertheless, we saw it in the exercise 1, that once we are at some point, here also the rounding error is present, but at some point the rounding error takes over. And then that has just an opposite behavior. It is something oscillating, and it has a slope that is here. That slope is going down, h to the power 2, so slope of 2. Here this is a slope of h minus 1. It is increasing, so the error gets larger as we take smaller grid spacings. And that is due to the rounding error. We have u of x plus h minus u of x. These get, we cannot distinguish x and x plus h at some point, and this difference gets 0. And then we have a full error there. Anyway, in this part the rounding error takes over. So be aware of that, because in some cases this is really important. Another problem, so that was exercise 1 that we studied here. Another problem, that another source of error is the iteration error. When we solve a linear equation, for example, a system of equation ax equal b, that we need, for example, for solving the Poisson equation, then we can do that iteratively. But then, when we iterate, we do not solve this linear system accurately. So we make an error when we stop the iteration at some point. Then we are not solving the linear system accurately. And that is what we studied in exercise 11. And then the error that we studied mostly in almost every exercise, that was the discretization error. We want to have a solution to one of our problems, and this numerical solution has an error. And this error, with respect to the exact solution of the PDE, that's discretization. As I said, almost all exercises. So actually this exercise, I wrote down everything. It was 4 to 12, except for, because we did not have an exact solution or a reference solution there, it was an exercise 10 for the heat conduction problem. So you see the importance of that. And that this part in the CFD community, that is called verification, to check whether we have implemented the numerical method correctly, and we are then getting a good approximation of the exact solution to the PDE. And the last source of error that we did not study, because we had at our disposal, luckily, mostly exact solution was the modeling error. Imagine we would want to compute flow around an aircraft that is turbulent. And for that, we are usually forced to use a turbulence model. And then we have to model that by some set of equations, and then we get some result, And then we can compare that result with the result in reality. And we imagine reality is what we measure in the wind tunnel. Also there we have some restrictions, but nevertheless that's a good way to get an idea of what is happening in reality. And that error then is the modeling error. So then here regarding the It's Learning homepage, there are a few announcements, and I'll come back to that before the break. Just the important thing is that we'll do tomorrow, that is the trial exam. So we have a trial exam ready for you, and you'll find that down here, and which will, at least part of it, we can go through all of it, but part of it we will go through tomorrow. So let's continue in the summary. And chapter 4 was on the numerical solution of ODEs. There we have looked at initial value problems for ODEs. Y prime is equal to our function f of ty. In the initial condition, y of 0 is y0. So that's an initial value problem for an ODE. And there we studied a couple of methods. And the one that we studied most was Euler's method. So just to remind you, yn plus 1, here the notation is in like in the community with the index lower index. In PDE the time would be the upper index. That is then the approximation, so the approximation at the new time level n plus 1 is equal to the one at the old one, plus the time step, which is here denoted by h, times the right hand side of the ODE at the old time level and with the old approximation. So, there we have done a couple of examples, and what is interesting here is, regarding the analysis, is the local truncation error. And a way to get that very quickly is by, in our case for the Euler's method, if we compute that at the time level n plus 1, then we take this, the method, the Euler's method, with the exact solution at the old time level. So then we take this here as y of Tn plus h, the ODE right hand side at the old time level, with the exact solution at the old time level, and we subtract the exact solution at the new time level, y of Tn plus 1. And then we can do Taylor expansion and get the local truncation error. So, and what we use there is that this here, according to our PDE, is equal to the y prime at the, sorry, I should be here careful, that is at y of Tn, because we assume that we have an exact solution. And important is that we assume for this analysis, just for the local truncation error, that the initial condition is at the old time level. So we assume here that we solve this. So for the local truncation error, we solve the ODE with the initial condition y of Tn is y, the exact solution. That just doesn't make sense. If you say yn. That is we start from the old time level. That's the catch, and that is also the name, the local truncation. It's the error committed from going from the old solution at the old time level to the new one. It's just one step. And that is opposed to the global truncation error. When we have the error at some time with respect to the exact solution of this PDE that we really want to solve. That is the global truncation error. The local truncation is just from one time step, one time level to the next. And here we find out, you can do that yourself, by doing Taylor expansion of this guy, that we get here minus h squared half second derivative of the unknown at the old time level plus and so on. So that means we have here an order h2 error, so second order. And if we know that, we know the global truncation error. The global truncation error we did in that notation was for En. En is then the approximation, the numerical approximation at time level n minus the exact solution to the problem that we really want to solve. For this, we start from the very beginning, go to the end time. And if this is of order h squared, this is one order lower. That's the rule. So for in our example here, that is for Euler's method, that is for Euler's method, and also what we have here, that is for Euler's method, it is one order lower. So the local one we can easily determine by Taylor expansion using this definition and these tools that I gave you, and from that we can conclude the global truncation. The other thing that we investigated there was stability. And we have actually an example of that in the trial exam. So therefore, I can be quite brief on that. So stability. For stability of ODE, we want to check whether perturbations that we have, always imagine rounding errors, if they are amplified by the numerical method or damped. If they are amplified, the numerical method is unstable. If perturbations are damped, the numerical method is stable. And we can find out that as we find out about the stability of an ODE by looking for the difference between two solutions. One without perturbation and one with perturbation. If we look for the difference, we get the Jacobian into play, and then we get the test equation. So we look for the test equation, and the test equation is y prime equal to lambda y, and the link to the ODE is that lambda is the Jacobian of the right-hand side, where we do the derivation with respect to y. So that is a scalar for a scalar problem. And if we have a system, then we would not have lambda equal to j, but lambda would be equal the eigenvalues of j. So that is what I write here is essentially for the scalar problem. And we have then the initial condition, simply 1. So we imagine we have in the beginning perturbation of 1. And then we see how that is amplified. And how we see it is by applying our numerical method to solve the test equation and find out the amplification factor. So we determine the amplification factor. And that was, we call that G of lambda h. Lambda is this lambda, and h is the grid spacing. t. And we find that when we plug in that and we compute the solution at the new time level with the numerical method and divide it by the old time level. Actually, with this choice here, it is the same as y1 over y0, which is 1, so it's y1. But this is not important. The stability condition is once we have the amplification factor, that we have to multiply each time the solution with that factor. So if we want to have that bounded, it's clear that has to be smaller or equal than 1, absolute value. So that is the condition. G of lambda h, absolute value has to be smaller or equal than 1. That is the condition. And then we looked for the, well, we would have to compute that, and in our example, we would just to plug in things here. So that would be yn plus h. This would be f of t, and yn would be lambda yn. So we would get h lambda yn. So that means this will be 1 plus lambda h. That is what we get for, this is what for Euler's method. And then we have to see whether when this condition is fulfilled, and for that we can use the stability domain with the real part and the imaginary part of lambda h. And it turns out that we have here a circle around -1. Here this is -2. And this is the stability domain of Euler's method. That is the set of all complex numbers for which this condition holds. So z is now lambda h. That means absolute value of 1 plus z is more equal to 1. That is then a circle around -1 with the radius 1. So this radius here is, this radius is 1. So then we can easily check whether our method is stable. In the case when lambda is real, it means then that lambda h has to be between 0 and -2. That is the condition if lambda is real. If lambda is complex, it's usually easiest to take the squared, because then we can take the real part squared plus the imaginary part squared. So that was the Euler's method. And another method that we studied was, but we can also identify that as the explicit Euler method, or forward Euler. And then there is also backward Euler, or the implicit Euler method. That is very similar to the explicit one. To get the approximation at the new time level, we take the approximation at the old time level plus the time step h times the ODE, right-hand side, evaluated at the new time level with the approximation at the new time level that we don't yet know. That makes so then this here depends on that. So that means we get a nonlinear problem if we have a nonlinear f. So there, it turns out it has the same global truncation error as the explicit Euler method. It is first order in H. And the stability domain is now much, much larger. The real part of lambda h, the imaginary part of lambda h. The lambda is the same as we discussed here. It's coming from the Jacobian of the right-hand side of the ODE. And here, it turns out that we have only a circle to the right that is at +1. This is 2, so should be a circle with a radius 1. Except for this circle, everything belongs to the stability domain of the implicit Euler method. So the stability domain of implicit Euler is the set of all complex numbers. Now we would have to determine the amplification factor. We skip the derivation, we just write what we would get. It is 1 divided by 1 minus z. So here would be the lambda h. That has to be smaller equal than 1. And so essentially for all values of lambda h except for the circle with radius 1 around plus 1, everything belongs to the stability domain of the implicit Euler method. So we had also looked at others, and in the exercises in the week before this, we also looked at the trapezoidal method. But we stop here. The next chapter, where we entered then the spatial discretization, was an overview over spatial discretizations. So after looking for the only time discretization, we looked at spatial discretizations. And there the focus has been on the finite difference method, clearly. Finite difference method. That is the contents of this course. However, I also gave you an idea, examples of the finite volume method, the finite element method, the spectral method, and spectral element method. Very rough, but that is was just for an orientation. But this is the key discretization that we have been using here. Chapter 6, we looked at the heat equation. Similar fusion equation, so whether we consider heat conduction or whether we consider diffusion, for example, of concentration, or we had also viscous diffusion. So we had some examples for that. So, and the equation that was then the key equation for us was the 1D heat equation. We also showed this 1D diffusion equation, where we have the time derivative of u is equal to alpha, the thermal diffusivity, times the second space derivative. So that is a parabolic PDE, and we have to give boundary conditions at all boundaries. Either directly, where we describe the value, or the derivative du dx, which is a Neumann boundary condition. We did not have Robin, but we could have, but we concentrated on directly and Neumann boundary conditions. The schemes that we studied were the key scheme, that's we start like that, was the forward time-centered space scheme. So that is a scheme that you should certainly know. Time-centered space. And instead of writing the scheme, I just give you the difference molecule, the stencil of the method. So if we have the j minus 1 and j plus 1, at the old time level, we determine the value at the new time level at j by using the values at the old time level at j and its neighbors. What we studied here was consistency. doing that, we have determined the truncation error. So then we replace the numerical approximations by the exact solution to the PDE. And we write it in the form that we can directly identify the time derivative. And then we get the order of accuracy. For this example, we get then that this is of order, first order in time and second order in space. That we see by computing the truncation error. So that is essential. And the other essential is the stability. For that, our tool is the von Neumann stability analysis. There, we usually write the equation, the finite difference equation, in a form that we have the unknown on the left and the known on the right. And then we insert a Fourier mode, u hat n e to the I k xj for ujn, and we find out from that that the condition that we also get an amplification factor, and that also has to be smaller or equal than 1, that condition is then satisfied for, in that case, when we have this condition, and the R here is the von Neumann number, that is the thermal diffusivity times the time step divided by the grid spacing squared. And the conclusion that we need in the end is convergence. Convergence means that the numerical solution converges to the exact solution of the PDE. And there our tool is simply the Lux equivalence theorem. That is same for linear initial value problem. That is consistent. So for consistent approximation of a linear initial value problem, stability is equivalent to convergence. That means when we have shown that the numerical method is consistent and stable, then we know it is convergent. If we have shown that the method is consistent, we can still use the Lux equivalence theorem to show that it is not convergent, because when we show that the method is consistent but not stable, then it is not convergent. And we have an example in the test exam on that. So that is important. When you are asked to show that the numerical method is convergent, you do these things, these 2 points, show that it's consistent, show that it's stable under a certain condition, maybe, and then you use simply state Lux equivalence theorem. For example, in this case, the FTCS scheme is convergent under this condition, because it is stable under this condition. Okay. Another example of the method that we studied for solving the heat equation was what we call the simple implicit method. You should be able to write that down and just give you the stencil. We have only the value at the old time level to determine the value at the new time level, but we take now the values at the neighbors. So then the different stencil is like that. So instead of using the approximation of uxx at the old time level, as we did for forward time-centered space, for the implicit method we use the approximation of uxx at the new time level. And that leads to a tridiagonal linear system. That we get a tridiagonal linear system. And well, you should know also about that, also how the boundary conditions enter. The truncation error is the same as for the forward time-centered space, but this scheme is unconditionally stable. So, unconditionally stable. And that means stable for all R, which is this loop around the larger equals 0. That means stable for all R greater equal to 0. And from that, we can then use again Lex equivalence theorem to conclude that it is convergent for R greater equal 0. So for any reasonable value, because alpha we have to choose positive to get a well-posed problem. And then delta t is of course positive and delta x squared also. So then our result is positive for, and then the method is always convergent. It does not say that it is accurate. Remember, that is something different. Convergent just means that in the end we converge to the exact solution when we refine the grid spacing and the time step. But it doesn't tell you for your chosen delta x and delta t that you get good results. That is another story. To get good results there, you need enough grid points. Delta x must be small enough. Time step must be small enough if you want to follow the time dynamics. So that is another story. But this tells you when you refine the grid spacing, delta x, and the time step delta t, then your numerical solution will approximate the exact solution. Okay. So before we take the break, I have a few points to discuss with you. First, regarding the trial exam, I already mentioned that we will discuss at least partly. We will not manage to do all tomorrow. We have it available, and I recommend you to have a look at that. And before getting those right, okay, and before you do it, look at the solution. Do it yourself. I think you learn most when you try yourself, because that is the situation that you also have in the exam. You have nothing to look at. You have only the only allowable aid that you have is an approved calculator. You don't need anything else. You probably don't need that either, but you can have an approved calculator. That's all. So try to do the trial exam without any help, and then you see where you need to fill up your knowledge at some points, and do that. The thing that is already announced, therefore I want to bring that up, is the question time on June 4. That was announced after the last meeting of the reference group. But in addition to that, Reda Christofferson and Jürgen Ohnes, the scientific assistant on the course, and me, we want to offer you a time to meet you. And Reda's proposal is to do that in the floor above Shell Cantina. Probably most of you know, otherwise I can give that. There is a place where there are boards and tables, and where you can sit and work. And our proposal is to meet you there on either Tuesday 2nd June or Wednesday June 3rd. So that are the options that are suitable for us. So we just write down that. Just a moment to think about it. that is June 2 or June 3. And our proposal is from 10 to 14 hours. So we will not be there all the time, but we will come by and then we can answer individual questions. The time that is allocated on June 4 is meant more for public questions. So when you come there, you have some questions, you ask it, and then either me or Radar, we will answer that question to all of you who are present at that time. But here it is meant that we go around and answer individual questions, maybe individually or a group of people working together. So that is the idea. So then let me ask you, this is a Tuesday, this is a Wednesday. For whom is June 2, the Tuesday, preferable? You see? For whom is June 3, Wednesday, preferable? 2. So then that is the majority. Is that okay? So then we take June, that will be Tuesday. I'll announce that then on It's Learning. And the other question that I have to you is regarding the lesson now. Yes?
Yeah, would it be possible to have the day before that? Because we have an exam on the 3rd. So neither day really fits for us.
Okay, then I understand. Okay. Well, yes, it is possible. The disadvantage is only that Radar will not be here. But I have to check with Jürgen. I'll be here, so for me it's possible. So then let me add then June 1. So we repeat the questioning. So the June 1. For whom is that date suitable? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, that seems to be the majority. Is that okay with the others? Or is there an objection? Do you have an exam on June 2, for example? Okay, so then we take that. Monday. Okay. So I've making the announcement. Regarding the lesson on Monday, lessons are scheduled as usual from 12 to 14, now on Monday, and from 18 to 20. Do you want to have this lesson or for feedback on old exercises, or because we have no new exercises to discuss, or shall we simply skip it so that there will be no lesson? And I hear opinions. That is the coming Monday.
I would like to have it.
For what?
For old exercises.
Okay, feedback then. Okay, yeah, that's okay. Shall we have both times, or is it enough from 12 to 14? So let's see the calendar. That is on Monday 20. Is that what we are talking about? So that is for exam preparation, and now feedback of old exercises would be then that would be now April 20, 12 to 14, so that is then, we do that. Question is now for 18 to 20. Please tell me if you don't raise your hand now, we skip it. Is that okay? Okay, so then we have this, we keep this, and then that will be then the last event of lesson for the whole course. The last lecture is tomorrow. Let's see if I have anything else. just a reminder, you should be approved of at least 9 out of 12 exercises by Tuesday 21. So that I announced earlier, that is this point here. Please note that you should be approved of having completed at least 9 out of 12 exercises by April 21. But I think that is already no problem for you who have been following the course actively. Is there anything more from your side regarding the administration? Then I have an addition, and that is course evaluation. I'll make a course evaluation available today, and I strongly ask you to do that course evaluation, to give us feedback for this course, and for us to be able to improve it for next year and the years to come. Okay, if there's nothing else, we take now 15 minutes.